So in this first problem, this is really an in-class exercise, so I would have you spend a little bit of time thinking about this one. So what I need you to do is, you've got these different criteria, and what you would like to do is to graph a piecewise function with these properties. So it has to be one function that has all these properties. You don't have to find a formula for the function. So let me give you a minute to think about it. Okay, here we are. So what I've noticed is these two bits of information, they each give us a point. Let me zoom in a little bit. Right, so let me just make some marks here. So this is going to be 1, 2, 3, 1, 2, 3, 1, 2, 1, 2. So I'm just going to put in some key information. That's 0. So I know that P of 0 is 2. So let me draw that on here. Let's choose another color. Let's say blue. Right, so there's a point, right? That would be P of 0 is 2. Then the other one is, I've got P of 2 is equal to 1. So that would be here. So those are definite points on our graph. So let me just make some markings. This is 2, this is 1, and this is 2. All right, the next things that we have to contend with are the parts that are in the middle here, these limit statements. Well, we notice that one limit is around 0, right? So we're doing something around the origin here. And then another limit is around 2. So I'm going to work with these two statements first. All right, the first one, let's look at the bottom one. It looks kind of easier to work with. I've got the limit as we approach 2 from the right of P of x is 1. So what I can do for that is, I can just draw a constant function, right? So that as I'm approaching 2 from the right, I'm all at the same height, the y value of 1. So that works out. But the next part is, we've got this one done. The next part is that P of x, though the limit at 2, it doesn't exist. So what are our possibilities? Well, we can have a jump, we can have a vertical asymptote, we can have some kind of oscillating feature there. I'm going to go with a jump, and I'm going to put it down here. Let's start at -3 just to give me some space. That means that I can't have two function values, right, the same, so one has to be an open circle, and then we have to figure out how to draw the function from there. So I'm going to put an open circle here. Now I cannot, so this would clearly give us a jump in the graph, right, as long as and the limit wouldn't exist, right, but I have to kind of see how do I connect, this half of the graph with that point. I can't draw a function to the right, or any kind of graph to the right, because it wouldn't be a function, it wouldn't pass the vertical line test. All right, so let's see. We're still working on this part, but we're almost there. The next thing is, we've got the limit as x approaches 0 is equal to 0. Okay, so the limit, we know the value of the function is 2. And I have to have the limit being 0, right? So I can't have two different y values, right, for an x value of 0. So I'm going to put an open circle there. And then I'm just going to connect. What if I connected this in this way? And then I can really do anything here. I can move it up, whatever I want to do, and we'll make it look like that. All right, so let's just verify here. Yeah, clearly, if we're around 2, then if I'm looking around 2, the limit from the right would be 1. The limit from the left, as I'm approaching 2, approaches -3, and we see the jump there. All right, then if I'm looking around the origin 0, I have an open circle here, but the limit, my y values are all approaching 0 from below. And here, if I'm approaching the x value of 0, my y values are all approaching 0 from the right as well. So I think this would be a pretty good one example, right, of a graph that would meet all these characteristics. Okay, let's take a look at another graph here. In a special function, it's called the floor function or the greatest integer function. So it's defined as, and floor, because we have, it looks like this. Okay, it's not quite in square brackets, and it's not absolute value. We've got these little legs kind of at the floor. So it's the greatest or the largest integer, right, that's less than or equal to x, whatever that value is. Well, first, let's take a look at what this graph might, how this graph, how we produce it in our calculator. All right, so let me scroll up for a second, and I'm going to start you off here. The first thing that we want to do is, I'd like you to just go to y equals in your calculator. And then you're going to click on Math, Num, and you want to go to the number catalog. So I have to go to Math, go to Num, and then you're going to click on 5, integer. That's the greatest integer. Since you went to y equals first, it should paste it into, y1. So we're going to paste that in there. So this is one of the greatest integer of x. Now I gave you a window. If you look on the handout, the window is from -3 to 3 in x and y. Then you can just press graph. Well, what happens when you press graph is that you get those vertical parts to the graph, and there really shouldn't be there. It's just how your calculator does it. So if you go to mode on your calculator, I've got a TI-84 Plus, and change it in mode to dot or thick. If you have an older calculator, just change it to dot mode. You might have to toggle on and off for it to work. Once you do that and then press graph, this is the function you should get. All right, so the things that we have to figure out on the worksheet, I have to figure out some, you'll notice, of these steps. So this is what's called a step function, right? So we've got these different y values, right, for different intervals of x. We have to figure out on which side is there a closed circle and which side there is an open circle. So that's what we're going to take a look at next. Right, well, first what we can do is, as we look at this, we can figure out from the graph what's happening, and maybe I'll draw the pattern, right? So we're seeing what the pattern is. There's an open circle here and a closed circle here. Okay, this one, there would be a closed circle here, right, and an open circle. So the closed circles are on the left and the open circles are on the right. That's what we're seeing. Let's see why this is so. So down here, I'm just going to do just an aside here and just do some work. So what if I want to find, the greatest integer, let's just say a 4.1. And then I'd like to find the greatest integer of, and I'm going to change this. Let's do 3.1 just because we see it on the graph there. I don't have to draw it. And then let's do of, let's say 3.01. And then let's do 3, and let's do 2.9. So we want to find the greatest integer of each of these. Now you could just put this in your calculator in the home screen. If you just did, in this case, I'll write it down, INT in the home screen now of 3.1. You can see what you would get, but that's what you do in your calculator. All right, well, let's take a look at the graph here. So if I'm at 3.1, remember, these are my x values. So I'm looking at the greatest integer of x. That's what I'm trying to figure out. 3.1, let's just say it's about here. Well, where would I be? I'd be at a height of 3. So we see the greatest integer of 3.1 is equal to 3. All right, what if I'm at 3.01? Well, I'd be about here then. Well, I'm still at 3, right? What's the greatest integer of 3? Remember, we're thinking of, we want the integer. So the integers are, when we take a look at integers, remember it's like -3, dot, dot, dot. You know, -2, -1, 0, 1, 2, etc. So the greatest integer of 3, it has to be less than or equal to it. It would be 3, right? That's the smallest integer that's either less than or equal to this. Now, what happens if we're at 2.9? So now I'm at 2.9, I'm over here. What happens? I jump to this other step, so now I'm at 2. All right, so now we can kind of fill in what's happening here. All right, I'm just going to write these values. Okay, so you're pretty familiar with finding one-sided limits. Now we're just dealing with it with a stepwise function. So in this case, check your work on this. You should be able to find these one-sided limits. The idea here, and hopefully that you're noticing, if I'm at an integer, right, if I'm to the left of it or to the right of it, these are x values now, I'm going to be on 2 different steps, right? So that's why we're seeing that this limit really doesn't exist, right, at each of the integer values, okay, because of these jumps. So, for example, you know, to the left of -1, if we're approaching -1 for the left, we're at a y value of -2. If we're approaching -1 to the right, meaning the x value, we're at a step, a height of -1. So we're seeing that these limits are not existing. But supposedly, what if I suppose that I'm on at 2.3 here? 2.3 would be right there, right on this step. If I approach this from the left or the right, I'm still on that same height, that y height of 2. So these would all be the same. All right, let's just take a look at the domain and range of this function. What I'm going to do is I'm just going to add a new page here. So I have a little bit more room, and I'll slide up. Okay, so let's take a look at the domain and then the range. All right, well, the domain for this function, we can have any value, right, for x. We can put into this formula, right, and we can find the greatest integer of it. So for this, we see it's all real numbers. Okay, so we would write all real numbers, or we would say -infinity to infinity. Take a look at what's happening with the range, though. What are the y values that we get out? All right, so if I'm trying to find the, you know, the greatest integer, we looked at 3 or 2.9. You notice, look at all these values, and even if I did some negative numbers, right, we'd move to the left always. So we're going to just get integer values out. So we actually just get a set of points, and I'm just going to indicate it like this, but it goes on forever. So -5, -4, -3, -2. And that would be the range of this. So we get these actual just discrete values. Okay, so let me zoom out. All right, well, I'm going to pause the video here so that you can kind of just think about this, go back, go over it, review it. And then when we meet up again in a short time, we're going to go on to techniques of computing limits.